In theory, the beginning of this section is all review. We'll see if it is. The base of the natural exponential function is e. This natural base can be used to assign a meaning to a general base. And the general basis is that's what you've done in the past, okay? So definition of exponential function to a base a. If a is a positive real number, not equal to 1, and x is any real number, then the exponential function to the base a is denoted by a to the x. Okay, so a number with an exponent that is a variable instead of an exponent that is a constant, and is defined by a to the x equals e to the natural log of a times x. Can anybody tell me why that definition actually does make sense? Yeah. Because if you think of it as e to the natural log of a to the x, when you raise a power to a power, you multiply the exponents, right? So that's how the x gets there. But look, the e and the natural log, they undo each other. So you're left with a to the x. Good. All right. Some things you need to remember. Anything to the 0 equals 1. When you multiply factors with the same base, you add the exponents. When you divide factors with the same base, you subtract the exponents. And when you raise a power to a power, you multiply exponents, just like you always have. Okay? Let's see. I think I'll skip that part. All right. If a is a positive real number, not equal to 1, and x is any positive real number, then the logarithmic function to the base a is denoted by the base a log of x, or log to the base a of x. I think you're supposed to say the logarithm of x with the base of a. You know, whatever. And it's defined as, and then they give us this horrible, horrible definition. Horrible, simply horrible. That must mean everything's different now. No, it doesn't. Okay? They're giving you a calculus E, that's a word, definition, but it's still, logarithms still work just like they did last year. Okay? So if you have the log of 1 to the base a, it's 0 because a to the 0 equals 1. All right? Since when you multiply factors with the same base, you add the exponents. When you have two things multiplied together, you can make it the sum of the logarithms. When they're divided, you make it the difference of the logarithms. See how it's the same idea as the exponent properties? Okay? And we did this one with the natural log a lot. The exponent right there, you can set in front as a coefficient. So it's the same properties. They look different now, but it's the same idea. Now, just like e and natural log are inverse functions, they're inverse functions because they're both to the base of e. Okay? As long as you have the exponential function and the logarithmic function with the same base, and now we're calling it a because it doesn't have to be e anymore, it's a. Any constant will do except for 1. 1 just kind of screws everything up. They're inverse functions as long as they have the same base. And if they're inverse functions, that means that if you take a base of a and you raise it to the logarithm of x to the base of a, the a and the logarithm undo each other, giving you x. And if you have the logarithm of a to the x to the base of a, they undo each other, leaving you with x. Because remember our definition of inverse functions? F of g of x has to equal x, and g of f of x has to equal x. Well, that's what they're trying to point out to you. Now, the logarithm you've dealt with the most in the past is called the common logarithm, and it's with a base of 10. Okay? So we'll still do some stuff with base of 10. So what we're attempting to do here is generalize the things that we worked with, the things we knew about, and the things we worked with, natural log and E, to work with any other base. Okay? Let's do a few examples, and I think you'll see that this is essentially what you did in the past. So if you turn to page 366, we'll do a few from your assignment. I'll begin with number 2. Evaluate the expression without using a calculator. So for number 2, we have the logarithm of 9 to the base 27, or the base 27 log of 9. Can you write 27 with a base of 9? Nope, I said that backwards. Can you write 9 with a base of 27? The base is 27. Can I write 9 as 27 to the something? 2/3. Because if I take 27 and I take it to the 1/3, which is its cube root, I get 3. And then if I square that, square the 3, I get 9. So that's 27 to the 2/3. Now, the logarithm, in the past, the natural log and the E would undo each other. So now the logarithm and the base undo each other, and we get 2/3. Number 8. Write the exponential equation as a logarithmic equation, or vice versa. On 8a, we start with a logarithmic equation. How do I know 8a is a logarithmic equation? It's got a log in it. Okay? So no big fancy reason. It's got log in it. All right, so don't look, don't look. All right, so what do we do here? Well, we take the base of 3 and we put the -2 on there because the logarithm equals -2. That means the exponent on the base is -2. Okay? Since the logarithm equals -2, then the exponent that goes on the base is -2. Well, what is 3 to the -2? 1/3 squared, which is 1/9. All right, so we changed the logarithmic equation into an exponential equation. On B, we're going to change an exponential equation to a logarithmic equation. All right, so let me show you doing it over here. So we've got the log of, what's the base? 49. Okay, what are we finding the logarithm of? The 7, and what should it equal? 1/2. Did this stuff last year? Yes. Trust me, you did. 16. Those of you that had Mr. Thaxton did this last year. I can't speak for those of you that didn't. I can't speak for any of you. Kim Sanity, really? See, I realized yesterday that I can call Ben Sanity. So I just drove him nuts with that last night. Because see, I'm of the sense of humor that thinks that if something's kind of funny at first, it's really funny like 1,000 times later. All right, let's take a look at 16. It says solve for x or b. So on 16a, we're going to solve for x. How do I know I'm going to solve for x instead of b? Because there's an x in there. Very good. You guys are sharp. So, for number 16, let's see here. We've got the logarithm of 1 over 81 to the base of 3, and that logarithm equals x. So doesn't that mean, close your eyes, doesn't that mean that 3 to the x equals 1 over 81? The base is 3, the logarithm, the exponent equals x, so that equals 1 over 81. All right, now, I don't mean to say this in a way that hurts your feelings, but this is exactly what they're doing in Algebra 1 right now. Now, they didn't start with that, but they're starting with that and solving for x. Write both sides with the same base. Can I write 80 or 1 over 81 with a base of 3? I can write 81 with a base of 3, right? 81 is 3 to the 4th. So 1 over 81 would be 3 to the negative 4. So what does x equal? I'll let you do b on your own later. Well, do it now. Because you're all going to, aren't you? That's just the kind of kids you are. Yep. Hooray! Everybody get it? All right. Let's try 18. Guess what we're going to solve for this time? Whew. Man. This class is just too easy for you guys. Your answer for A look anything like that? Bet you can't do 18B. We cool? Number 20. Now we're still solving for x. No, wait a minute. 20. Yeah, okay. My bad. I was looking at the wrong thing on my paper. All right, on number 20, we're still solving for x or b. For part A, it'll be x. All right, but look, this is quite a bit more complicated looking, right? So, let's use some logarithm properties to get us started here. The sum of those logarithms can be the logarithm of that product. Like we did when it was natural log, just because the equation is read left to right doesn't mean it has to be used left to right. This one we're kind of going right to left. We're taking the sum of the logarithms and making it the logarithm of a product. Okay? Well, that helps a little bit. Remember also what we would do when we would exponentiate both sides? Let's try that. But instead of a base of e, we should use a base of 3. So instead of e-ing both sides, we're 3-ing both sides. That is cool. So, on the left side, what do the base and the logarithm do to each other? So we get x times the quantity x minus 2 equals 3. Well, we can solve that. That's a quadratic. So we distribute the x to get it into standard form, which is everything on one side, 0 on the other, descending order of exponents, first term positive. Can we factor that? Yeah, that one's factorable. So we get the quantity x plus 1 times the quantity x minus 3. Bless you. And that means we get x equals negative 1 or x equals 3. All right? Then I wrote x equals negative 1's not in the domain. And I can't remember why it's not in the domain. I know the natural log's only defined for positive numbers. We didn't define this that way, did we?
Yeah.
Yep. There we go. Any positive real number. All right. We good? Try B, 20B. Did you get something like what I got? Questions? Questions? It didn't. I tinned both sides. I exponentiated both sides using 10 as the base. It's not as fun to tin both sides as it was to E both sides. I don't know why. The thrill is gone. All right, now does it make sense? All right, let's give 23 a try. Solve the equation accurate to 3 decimal places. So we're going to use our calculator this time. So we have 2 to the 3 minus z equals 625. Now, in the last 2 examples, we exponentiated both sides so that we got rid of the logarithm in the equation so that we ended up with a normal kind of equation with no logarithms in it. Well, this time, we've got an exponential function. Now think back, when we were dealing with e and we needed to get rid of it, what would we do to both sides? Take natural log. We can still do that. We can take the logarithm of both sides, and really, since we're going to use our calculator, it doesn't really matter what the base is. As long as it's a base, our calculator will handle. Okay? So keeping that in mind, I'm using the natural log because I know where that button is on my calculator, mostly. Okay? So no good reason I chose natural log other than I know how to do that on my calculator. Now, by choosing the natural log instead of a logarithm with a base of 2, if I chose a logarithm with a base of 2, I could work it out a little bit differently, but then I'd struggle mightily on my calculator. I don't even know if my calculator would do that. I don't know. I've never tried it. Okay? I can do this, though. Use our logarithm properties here on the left. Turn the exponent into a coefficient of the logarithm. Keep the objective in mind. I'm trying to solve it for z. So I'd like to get z all by itself. What's the next thing I can do that helps get z all by itself? Divide. Divide both sides by the natural log of 2. All right, and then to get z all by itself, if I add z to both sides and subtract the natural log of 625 divided by the natural log of 2 from both sides, I get z all by itself. All right, now, let's see if I can type all this in right. 3 minus parentheses, natural log, 625, close the parentheses on the natural log, divided by natural log 2, close parentheses, close parentheses. I think that ought to work. Into 3 decimal places, negative 6.288. All right, you with me? Questions? Okay. Well, this is calculus, so let's take a derivative or two. What do you say? No? All right, so this is back on page 362. We have some derivative formulas. So derivatives for bases other than e. Let a be a positive real number, not equal to 1, and let u be a differentiable function of x. So first one, the derivative of a to the x equals the natural log of a times a to the x. I usually write it the other way around because that way I can write it without parentheses. Okay? Well, if that's the case, then it's only fair that the derivative of a to the u being a function, would be the natural log of a times a to the u times the derivative of u. Okay? Chain rule, right? With me? The derivative of the logarithm of x to the base a is 1 over the natural log of a times x. And again, a lot of times I do that so I can write it without a parentheses. Does it really matter? No, it doesn't matter. And then the chain rule version. Life just got more complicated, didn't it? Yeah. Darn it. Yeah. Now, one of the first things we learned about derivatives, first we did the definition, and then the first rule, shortcut kind of thing we learned was the power rule. And you probably thought it worked for everything. But at first it worked for integers, and then it worked for rational numbers, and now the book's letting us know it works for real numbers. So I just taught it to you that way, okay? But there has been a progression. It does work for all real numbers. As long as the exponent is a real number, none of that I jazz. As long as it's a real number, then the power rule works, okay? Note, be sure you see that there is no simple differentiation rule for calculating the derivative of y equals x to the x. In general, if y equals u of x to the v of x, you need to use logarithmic differentiation. Now, logarithmic differentiation, like this. We don't know how to handle that, okay? Because we can handle it if the base is x and the exponent's a real number. We can also handle it if the base is a constant and the exponent is a variable. But what we can't handle is when the base is a variable and the exponent is a variable. So there's something called logarithmic differentiation, which is simply a way of rewriting the function. How often have we rewritten functions before we did derivatives or integrals? A lot, right? So it's another technique for doing that. So what you do is you take the natural log of both sides, use your logarithm property, then you have to use implicit differentiation because y is a function, not a variable. So the derivative of the natural log of y is 1 over y times the derivative of y. Right there. Over here, you use the product rule, first function times the derivative of the second, plus the second function times the derivative of the first. Then multiply both sides by y, so that you have y prime by itself, and that's how you have to do that. So if you're faced with a situation where your base is an exponent and when your base is a variable and your exponent is a variable, you've got to use logarithmic differentiation. Do you think logarithmic differentiation might be useful in other ways as well? Never? Never say never. That saying has always driven me nuts. So the never's canceled out? Right, so it's worse. Yeah. That's like when somebody tells you there are no absolute truths, except for there are no absolute truths. It is deep. Number 38. Find the derivative of the function. So here on 38, we have y equals x times 6 to the negative 2x. All right, product rule. First function, x, times the derivative of the second. Okay, the derivative of the second, that's an a to the, a to the u, isn't it? So it's a to the u times the natural log of a times the derivative of u. The book wrote it this way, I think. So that's the rule I'm using. You with me? All right. That's just the first half of the product rule. Ooh, wonder what I'm forgetting. Oh, yeah. Plus, second function times the derivative of the first. the derivative of x. And then the rest of it is mopping up. So in front of the plus sign, I can multiply the x times the negative 2 and make that a negative 2x times the natural log of 6 times 6 to the negative 2x plus 6 to the negative 2x. And I can stop there. Or if I want a more bookish answer, what would I do? Factor out the 6 to the negative 2x. $44. All right, on 44, I need to do some rewriting with logarithm properties. Because like we did with natural log, how we could eventually break it into small enough pieces that that each piece was kind of easy to differentiate, let's do the same thing. So let's make it the logarithm of the numerator minus the logarithm of the denominator. Keep the base 3. And then the logarithm of that product, the product of x and the square root of x minus 1, let's break that into the sum of the logarithms. And that square root of x minus 1 can be thought of as x minus 1 in a parentheses with an exponent of 1/2 on it. And then we can set the exponent in front of the log, like so. All right, if we have the natural log, nope, not natural log. If we have the logarithm of x to the base a, its derivative is 1 over the natural log of a times x. So the derivative of the logarithm of x to the base of 3 is 1 over the natural log of 3 times x. All right. For the next one, keep the 1/2. Make sure I write this right. All right, so when we have the logarithm of u to the base of a, we get, for our derivative, we get 1 over the natural log of a times u times the derivative of u. So we've got the 1/2 from the constant multiple rule. Then we've got 1 over, well, I'm using that 1 as the 1 over the natural log of a, so the natural log of 3, times u, so times x minus 1, times the derivative of u. The derivative of x minus 1 is 1. And then last, minus, well, I don't know what number the logarithm of 2 to the base of 3 is, but I know it's a number. It's a constant, isn't it? And the derivative of a constant is 0. So to make it look a little nicer, that's what we get. And if you want to go ahead and get one expression out of that, one rational expression, that's how you do it. Because I want that on there.